In this second part of the series, I will demonstrate how Manim brings a dynamism to the objects we placed in the canvas. But before we delve further into this, let's ensure we are on the same page. If you haven't done so yet, I recommend watching the previous video where I discussed how M-objects are defined and most important of all, what these M-objects are and their role in Manim animations. I also covered the importance of points in transforming any object in Manim. The coordinates of these points determine how an object appears on the canvas. So, without further ado, let's jump right in. In Manim, the canvas stretches from -4 to 4 in height and from -7.1 to 7.1 in width. Well, approximately. Consider this canvas as a camera frame with a height of 8 units and a width of approximately 14.2 with an aspect ratio of 16:9. Everything we want to capture must fit within this frame. This camera frame itself is an M object, meaning all the functionalities that apply to M objects also apply to the camera frame. We can zoom in or zoom out by resizing it using the dot scale function. This essentially simulates moving the camera closer to or farther away from the scene. Now, the question arises, how do I place an M object in this frame? Well, you see, placing an object within this frame is pretty straightforward. After adding an object to the canvas, we can position it at our desired location using the .move_to function or .shift function. Now, Manim also provides shorthand methods for positioning objects. For example, to place an object near any edge of the canvas, we can use toEdge function, and to set the spacing from the edge, we can use the buff argument. Similarly, the toCorner function positions an object at a specified corner of the canvas. Now, with these tools in hand, we can easily transform animate objects within the canvas, which enhances the dynamism of the animations. Let's take another look at these points and their roles in the Bezier curves. Remember anchors and handles? To develop an intuition on how to access these points, let's focus on this square. Manim provides intuitive functions like get top, get right, get bottom, get left, and get center to get the coordinate of these points. Now just take a guess, a simple guess, whether the written values of these functions remain the same when I rotate the square by 45 degrees. This happens because these functions are designed to maintain the sanctity of the shape and the properties of the M object. You can observe the difference when I apply the draw creation then fill animation to the original and rotated versions of this square. These points play a crucial role in defining what animations are and transformations of the shapes such as moving, rotation, and scaling of these shapes. The positions of these points dictate how and in what order animations emerge on the canvas. For instance, Manim includes various predefined animations, each serving a specific purpose in directing your animations. These points not only define how an M object is animated, but also influence the overall behavior of the animation. Understanding and utilizing these points allows you to create dynamic and visually appealing animations in Manim. To transform objects, we can use the animate function. Whether we want to shift, move, rotate, scale, or even transform them from one shape to another, animate is very handy. But what if we want our object to behave in a certain manner, in a certain specific way? For example, let's say we want a ball to change its direction whenever it collides with the wall. Here's how we can achieve that. To implement this in the code, we will need to use a combination of transformations and conditions. Manim allows us to create custom animations by defining behavior and interaction programmatically. For instance, to make a ball bounce off the wall, we can define its motion path and update its direction upon the collision. To implement this idea, Manim has this addUpdater function, where we input these set of rules in the form of a function. What addUpdater does is it calls these set of rules, at every frame of the animation. That is, after every dt seconds, the rules execute on the object, where dt is 1 divided by the frame rate. Let's first define the environment in the construct method. Then I define the function updateSquare, and inside this function, I set up the rules. Let's start with the simplest rule. At every frame, I want my square to move one step to the right, and then I will update the frames for 5 seconds as self.wait 5. You see, every dt seconds or at every frame, we are watching this square moving to the right. The square is moving too fast. Let's slow it down a bit. To do that, I set it to 0.05 step to the right. This seems smooth. If I want it to rotate as well, I can write another rule to rotate -2 degrees at every frame. Now it is rotating and moving at the same time. Consider another scenario that I need a circle which has to be always one step below the square. And that means circle needs its updater function as well. It can also be done by using lambda function as lambda c dot next to the square, and then I will define the argument where the circle has to be beside the square. Is it up, down, right or left? And the buff is the spacing from the square. Now we can bring out the same output by defining circle.always.next to with argument square, down and buff1 in place of addUpdater function. The functionality of always is inherently adding the updater function for us. If I define another scenario where the circle's diameter follows the width of the square, instead of changing the object by an absolute value, this time the circle's size depends on how the square's width is changing. That is, one object depends on another one. We use falways like circle.falways.setWidth square.getWidth. Notice that there is no parenthesis after square.getWidth. Having set the intuition of what updater function looks like, we are ready to go and demonstrate the collision of the ball. First, I define bouncing ball scene class. Vx and Vy are the speeds of the ball in the x and the y direction. And to make them accessible throughout the class, I define them as ball's attributes. Now, I want my ball to change its direction of movement whenever it gets collided with the wall. If the collision is from the vertical wall, speed in the x direction should reverse, and if the collision happens from the horizontal wall, speed in the y direction gets reversed. To ensure that the ball remains within this box, I need to confine ball's movement in the x direction within these vertical walls, and similarly in the y direction, ball shouldn't go beyond these horizontal walls. To implement this idea in the update ball function, I need all the 4 corners of the ball. Here 0 and 1 are the indices to access the x and the y coordinates. Using the simple if statements, I define what should be the ball's speed in each direction at every frame, and I'm going to shift it by that amount. In the first if statement, ball's movement along the x-axis is confined between -width by 2 to +width by 2. And going with the same logic, in the second if statement, ball's y direction movement is confined between -height by 2 to +height by 2. Seems promising enough, isn't it? Well, we can also play with the physics here by defining the collision impact. And now, let's come to the real meat of this video, the rules pattern. The parametric equation of Rose pattern is R equals to A cos k theta, which is in Cartesian coordinates transform as x is a cos k theta and y equals a cos k theta sin theta, where k here is just a parameter which defines the number of petals in the rose pattern. These Cartesian equations help us defining the points of the rose pattern. So first I define the class rose pattern, and this class inherits all the features from a VM object. Now in the init method, let's give parameters like radius, k and quarks, like all the other parameters, for example fill color, stroke color, etc. for all the other things. In the parametric equation, theta goes from 0 to 2 pi, and we need a step size which is equivalent to how smooth the curve do we want. Lower the step size, more the smoothness. So points are arranged as a 2D array. Using list comprehension method, lines from 10 to 16 describes all the points of the rose pattern with the parameter k. And then the last step is setting these points smoothly, which I covered in my previous video. Now let's see the code in action by defining the scene class. Using the animation show creation or any other type of animation, do we create such petals? I think we should colorize it. I am using setColorByGradient function to colorize my rose pattern. To define the gradient of colors, I am using blue, white and blue color as my argument. This is how rose pattern with k equals 10 looks like. Now, to avoid defining this rose pattern repeatedly, I define a function getRosePattern. Let's go a level up and bring the dynamism in the k value. I am going to animate different rose patterns with their k values increases from 0 to 10 with the step size equals to dt. Now to bring the smoothness in the animation, the step size has to be small. Any guesses how can we do that? Adding an updater function to the rose pattern. There are many ways to implement that. One of the traditional way is to increase the value of k after every frame, just like we were shifting the ball using the speed variable. So wait time would be 10 seconds. But this is taking a cumbersome approach of calculating the increment after every frame. Assume that we need the runtime of 20 seconds. Then the increment value gets changed to dt by 2. If the runtime is 5, then the increment is 2 dt. We can avoid this boring calculation by defining a variable and track its value at each frame. We can implement this idea using value tracker. Value tracker is an M object to encode some number which we can use it to change the object's property. Let's see a demonstration in action. I define kTracker as value tracker and the argument goes to be 0. And to get the value from the value tracker, we use getValue function. Similarly, for setting any value to this value tracker, I will use setValue function. Our usual update function goes like this. Everything is similar. The only factor changes is how we are using a tracker to track the changes in the k value. Besides that, there is one more way to implement without explicitly defining the update function is by using updateFrom function. The functionality of updateFrom func is similar to falways. Now, there is one more thing that I want to play it with, is the increment rate of k. For now, the increment in k is predetermined by the Manim. To set it to a different rate, I need to use the for loop and wacom function to animate the transformation with the runtime equals to the rate of the increment. Before I end this video, I want to demonstrate all the rose patterns in a nutshell, just to give you an intuition how different k values bring out the beauty of the mathematics. And to implement this, I'm using arrange in grid function. Well, that's all it for now, but I had so much to share about Manim. In the next video, we will explore how to add text in the canvas on the screen and transform it to suit your needs, including changing fonts and styles, making it bold, italic, changing the colors, and how to write equations using the latex, how to make graphs using parametric curve. And did you know that we can also define the rows pattern with parametric curve? So stay tuned for the next video. Wait, if you have made it to this point, I would like to take a moment to thank you for watching. And if you think you have learned a thing or two, you can support the channel by various ways. One of the best ones is by sharing this video and subscribing to the channel. It is free for you, but it encourages me a lot. Thanks again. See you in the next video.